Do you think it could be that one of the most fundamental aspects of our lives is nothing more than a complex illusion? Time, the omnipresent force that apparently governs our existence and dictates the rhythm of our lives, is not what it seems. For example, time appears to be slowed down for an object moving close to the speed of light. And it flows at different speeds depending on the strength and the gravitational field around us. Have you ever considered that time may be just a figment of our imagination, a construct invented by our brains to make sense of the world? In search of the truth behind this mysterious concept, you'll have to step into the unknown and question everything you thought you knew about time. What is time? Time, in its simplest form, is a tool we created to measure, change, and put order into the complex events that make up our lives. Our ancestors needed a way to keep track of natural cycles, such as day and night or the changing of the seasons. This was crucial to the coordination of activities such as farming, navigation, and religious rituals. Early methods of timekeeping were based on natural phenomena such as the rising and setting of the sun, the phases of the moon, and the position of the stars. As human society became more complex, so did our methods of measuring time. We developed tools such as sundials, water clocks, and finally mechanical clocks to divide the day into smaller and more manageable parts. Calendars were created to track the passage of longer periods, such as months and years. Different cultures have developed their own unique calendars and timekeeping systems, reflecting the diversity of human understanding and interpretation of time. While timekeeping systems help us manage our daily activities and long-term planning, the perception of time remains a deeply personal and subjective experience. Our brains process and interpret time differently depending on factors such as age, emotional state, and cultural background. This suggests that time is not a specific universal phenomenon, but rather a flexible construct that we shape according to our individual experiences and needs. Despite its ubiquitous presence in our lives, time remains a somewhat illusory concept. This raises the question, is time an objective reality, or is it simply a construct we've created to order the chaos of our existence? History of time. So, let's delve a little deeper into history. The traditional understanding of time as an independent, constant entity was challenged by a groundbreaking work from the early 20th century, by Albert Einstein. Einstein's theory of relativity introduced the concept of time as a dimension, forever changing our view of this mysterious phenomenon. Einstein's theory of relativity emerged from his work on the nature of light and the concept of absolute space and time, which was central to classical physics. He proposed that the laws of physics should be the same for all observers, regardless of their motion relative to each other. This revolutionary idea led to the development of two interrelated theories: the special theory of relativity and the general theory of relativity. In the special theory of relativity, Einstein demonstrated that space and time are not separate entities, but intertwined in a single continuum known as space-time. In this four-dimensional structure, time becomes the fourth dimension, and events are represented as points in space-time. This concept shattered the traditional view of time as an independent variable. By showing that it is an integral part of the fabric of the universe, Einstein's theories also showed that time is relative and dependent on the observer's frame of reference. According to the special theory of relativity, two events that appear to be simultaneous to one observer may occur at different times to another observer, moving relative to the first. This phenomenon, known as simultaneity relativity, challenges our perception of time as an absolute and constant entity. The general theory of relativity extended the ideas of the special theory of relativity to include gravity in the picture. In this theory, massive objects such as planets and stars cause space-time to warp. And this warp is perceived by objects moving within it as gravity. The presence of a massive object can also affect the flow of time, leading to a phenomenon known as gravitational time dilation. In the special theory of relativity, time dilation occurs when two objects move relative to each other with considerable speed. The faster an object moves, the slower time flows for that object compared to a stationary observer. This effect becomes more pronounced as the object approaches the speed of light. This phenomenon is best illustrated by the famous twin paradox, where one twin travels at near the speed of light while the other stays on Earth. Upon return, the traveling twin will be younger than the Earth twin because of the time dilation. In general relativity, time dilation is also due to the influence of gravity. Time flows more slowly in stronger gravitational fields, for example, near massive celestial objects such as planets or stars. This effect has been experimentally tested using atomic clocks placed at different heights. Clocks closer to the Earth's surface, where gravity is stronger, run slower compared to clocks at a higher altitude, where gravity is weaker. The slowing of time, while seemingly illogical, has been confirmed experimentally and has practical applications. An excellent example is the Global Positioning System (GPS). Satellites orbiting the Earth experience time dilation based on both velocity and gravity, which must be taken into account to maintain accurate timekeeping and location data. In addition, experiments with high-speed particle accelerators have confirmed that particles traveling at near light speeds experience significant time dilation as predicted by the special theory of relativity. Relative nature of time. Before Einstein's theory of relativity, time was assumed to be unchanging in a universal background for all events in the universe. Sir Isaac Newton, for example, believed in the concept of absolute time, which flows uniformly and independently of the events he measures. However, the discoveries of time dilation and the relative nature of time in both the special and general theories of relativity challenge this concept, demonstrating that time is not a constant but a variable, depending on the motion of the observer and the surrounding gravitational field. The traditional view of time as an absolute entity also assumes a strict adherence to causality, where cause always precedes effect. However, the relative nature of time in relativity theory suggests that the order of events may depend on the observer's frame of reference, which can lead to situations where cause and effect may appear to be reversed or simultaneous. This challenges our intuition. Understanding of causality forces us to re-evaluate how we think about the evolution of events in the universe. The concept of the arrow of time, the idea that time flows in one direction, from past to future, is deeply rooted in our understanding of the world. It has also been challenged, however, by the findings of relativity theory regarding the relative nature of time and the potential reversal of causality. These prompt us to reconsider whether the arrow of time is a fundamental aspect of the universe or simply a construct of human perception. Since the traditional view of time as an absolute entity has been undermined by the discoveries of relativity theory, some scientists and philosophers have suggested that time may be an emergent property rather than a fundamental aspect of the universe. From this perspective, time arises from interactions and relationships between objects and events, rather than existing independently. Quantum mechanics. Leaving behind the challenges of Einstein's theory of relativity, we venture into the even more confusing world of quantum mechanics. In this realm, the nature of time becomes confusing and elusive, as the rules governing the quantum world defy our everyday understanding. Quantum mechanics is a branch of physics that studies the behavior of particles at the atomic and subatomic levels. It's governed by a set of probability rules that are markedly different from the rules of classical physics. In the quantum world, particles can exist in several states simultaneously, a phenomenon known as superposition, and their properties are defined only when they're measured or observed. The concept of time in quantum mechanics is very different from the concept of time in classical physics. While classical physics describes time as a continuous and absolute entity, quantum mechanics treats it as a discrete quantized parameter. This leads to situations where it seems that time loses its traditional meaning and takes on a more abstract role. Now, to illustrate, let's consider the following everyday scenario. You observe animals in the wild and notice they behave differently when they know they're being watched. The closer you get to them, the more their behavior changes, making it difficult to understand their natural state. This example illustrates the observer effect in quantum mechanics, also called the Heisenberg uncertainty principle. In the context of quantum mechanics, the observer effect refers to the idea that active measurements or observations can disturb the state of a quantum object, such as an electron, just as your attempt to observe animals in the wild affects their behavior. Observing or measuring a quantum object can affect its properties, such as position or momentum. Heisenberg's uncertainty principle states that it's possible to simultaneously know the position and momentum of a quantum object with absolute accuracy. The more precisely we measure one property, the less precisely we can know the other. In the quantum world, the very act of observation or measurement can lead to the collapse of the wave function of a particle, and the transition from the superposition of many states to one definite state. This process is inherently probabilistic, and the result cannot be predicted with certainty. Taking into account the phenomena of quantum superposition and observer effect, it becomes obvious that our traditional understanding of time as linear progression may be wrong on the quantum level. Instead, the quantum world offers a more fluid, interconnected view of time, where the boundaries between past, present, and future are not as rigid as we once thought. The block universe, as we've seen, our understanding of time is closely intertwined with our understanding of space. In this complex relationship, many theories attempt to explain the nature of space-time. Among these theories, one stands out as particularly intriguing and thought-provoking: the block universe theory. The block universe theory, also known as eternalism or the space-time block view, is a philosophical concept that stems from our understanding of Einstein's theory of relativity. According to this theory, past, present, and future are not separate entities, but part of a single four-dimensional structure called space-time. In this structure, all events from the origin of the universe to its possible end coexist simultaneously. To better understand the theory of the block universe, we must first understand the concept of space-time. In Einstein's theory of relativity, space and time are intertwined, forming a single continuum. Space-time can be thought of as a vast four-dimensional block containing every event that has ever happened or will happen. In this situation, time is not a separate dimension that flows linearly, but rather an integral part of the space-time structure. Each point in space-time represents a unique event, and all space-time encompasses all possible events. Consequently, past, present, and future coexist in a block universe, turning our perception of time as a linear progression into an illusion created by our limited perspective. In the block universe theory, observers play a crucial role in the perception of the flow of time. Our perception of time as a linear progression from past to present to future is the result of the movement of our consciousness along our world lines, the paths we trace in space-time. Although all events exist simultaneously in the block universe, our subjective sense of time is limited to a single point on our world line, the present moment. This subjective sense of time can be likened to reading a book. Although all the words and sentences exist simultaneously on the pages, our perception of history is sequential, revealing one word at a time. Similarly, the events of our lives unfold as we cross our world lines within the block universe. Block universe theory also raises thought-provoking questions about the nature of free will. If all events, including our thoughts, decisions, and actions, are predetermined and exist simultaneously in space-time, does this mean that our choices are predetermined and free will is an illusion? This question has been the subject of heated debate among philosophers and scientists alike. Some argue that the existence of free will is compatible with the block universe theory, since our choices can still be determined by our internal processes, even if the results are already fixed in spacetime. Others argue that a block universe implies a deterministic universe, where our actions are simply the result of the laws of physics, and the concept of free will is an illusion. Not only does the theory of the block universe challenge our understanding of time and causality, but it also raises profound questions about the nature of reality itself. If all events coexist in spacetime, does this mean that reality is a static and changing structure? Or is our perception of reality, including the subjective flow of time, an essential aspect of the universe that cannot be separated from the objective structure of spacetime? These questions go to the heart of our understanding of the nature of existence. By exploring the implications of block universe theory, we may be forced to re-evaluate our perceptions of time, causality, free will, and reality itself, opening the door to a new understanding of the fundamental nature of the universe. Conclusion: in our daily lives, we rely on the passage of time to structure our activities, make sense of the world around us, and create meaningful accounts of our experiences. Time allows us to perceive change, growth, and decline, and to make predictions guided by past events. At the same time, our study of the nature of time has shown that our perception of time as a linear progression may only be a simple illusion, a product of our limited perspective in the vast fabric of spacetime. The paradoxical nature of time is a fascinating enigma. Time is both an important aspect of our lives and a construct that may not exist as we perceive it. Either way, we must remain open to new ideas and perspectives. It's through our curiosity, our willingness to question the nature of reality, and our relentless pursuit of knowledge that we will continue to discover the mysteries of time and the universe itself.